Hi, the purpose of this video is to introduce you to some arguments and techniques for proving things in linear algebra. I hope this will give you some insight and also some ability to do these arguments. There are certain mechanical techniques involved and certain ways of thinking that you can learn, and it takes time, but I think the more exposure you have, the more you can follow this. Okay, so I'm going to deal first with this proposition here. This proposition says, suppose S and T are subspaces of Rn. Okay, so imagine that you know what a subspace is, and it looks like a plane or a space. It's kind of a linear set within Rn. And we're supposing that the dimensions of these two, the dimensions of these two subspaces are the same. All right. And also suppose that S is contained in T. Then S equals T. Now think about this in terms of subspaces and spaces that you know. For instance, in 3 dimensions, a subspace would be a plane through the origin. Now, if you had another plane inside a plane that has the same dimension, that's obviously the same plane. Similarly, if you have a line inside a line, that line must be the same. So you can see this intuition here. Now, this is not at all obvious because just because something's a subset doesn't mean it has to be equal. It comes from the fact that these are subspaces, which are linear subsets. They're closed under linear combination. And you can use that fact to show that if they have the same dimension, that is the same number of linearly independent vectors, then they are actually the same space. Okay, so if one space is contained in another and has the same number of linearly independent vectors, that is the same size of basis, then it's actually the very same set. So this is actually important in many different proofs and theorems throughout linear algebra. So I want to spend some time to talk about this. Now, when you talk about dimension, usually talking about basis is not far behind. So one way to approach this kind of theorem is to express everything in terms of basis. Okay? So we know that if the dimension of S is equal to the dimension of T, then S and T have bases of the same size. So I'm going to say that the dimension of S and the dimension of T is equal to n, and so S1 through Sn is a basis of S, and T1 through Tn is a basis of T. All right. Now, what does it mean that these are a basis? That means that everything in T is a linear combination of these vectors. Everything in S is a linear combination of these vectors. Okay, so since S is contained in T, every one of these basis vectors in S is also in T. So every basis vector in X can be expressed as a linear combination of the vectors in this basis of capital T. Right? So I can write this out in summation notation. I have the n basis vectors of S here, and these can all written in terms of linear combinations of the basis vectors of T. Now notice that I need a different linear combination for each S. I didn't write the limits of the sum here. Usually when you just write the index, it's understood what the limits are. Okay. So in fact, since there are n different vectors T, there are going to be n coefficients here. Now I put the, so for S1, I have Cj1, for S2 I have Cj2, ... for Sn I have Cjn. So there are n different coefficients for each of these linear combinations. Now it looks like we're going to arrange those coefficients in a matrix, and in fact we are, but we'll get there in a moment. All right, so let's go to this key fact that what we have here is a linear combination of vectors, and we can express that as a matrix vector multiplication. Okay, very important fact, very important reconceptualization of linear combinations of vectors. All right. So the vectors are the T's, and these can be envisioned as columns of a matrix, and then the C's are the coefficients. So I can rewrite this first equation here. The column vector S is a linear combination of the column vectors T. I can arrange these column vectors T in a matrix, and I can arrange the coefficients as a column vector. I can do the same thing for S2 all the way up to Sn. Okay? So this notation means that I make a matrix out of the columns of T. This here, since the C's are constants, this is simply a column vector. Okay? And this equation here is expressing the very same thing that this equation here is expressing. Okay? And similarly with the other equations. All right? Now, I'm getting s in terms of t. Where am I going with this? I want to get the t's in terms of s. If I can show that all the t's are linear combinations of the s's, that means that every basis vector of t is inside of s, which means that all of t is inside of x. So that's the strategy. I want to go the other way to get the t's in terms of s's. But now I've set up these different equations. I want to put these equations together into a single equation. Okay? In fact, when you multiply matrices, you multiply them column by column. So I can put all of these together into a single matrix equation. This one is the first column of this matrix multiplication. This is the second column, and so on. Okay? And these are the columns of the result. So I put all of this into a single equation. So you started out with numerous equations. Now we ended up with one single equation in terms of matrices. So I'm going to call this matrix of S basis vectors MS. I'm going to call this matrix of T basis vectors MT. And I'll call this matrix C. Now, what do we know about these two matrices? Well, they're both of rank n. Why is that? Because the columns of MS are the basis vectors in S, and they're linearly independent. The column vectors of MT are basis vectors of T, linearly independent. Okay, so you may notice that there was just a glitch in the video because I realized that my argument was not correct. So what we have here, let's recap here, we've got MS equals MT plus C. MS consists of the columns of MS are the basis vectors of S. The columns of MT are the basis vectors of T. And then we have this matrix C. Notice that C is a square matrix, n rows and n columns. So MS and MT are both of rank n. What about C? All right, C is n by n. Now if C has rank n, that means that C is non-singular. So the question is C singular or non-singular? That's the question. If we can show C is non-singular, then it has an inverse, and that's going to help us. But that's what we need to see. That's the big question now. Is C singular or non-singular? That's the big question. Okay. All right, so let's go and suppose. So we're going to prove by contradiction. That's what this supposes. This is proof by contradiction. So we'll just say, right? So this is proof by contradiction, so I'm going to highlight that. C is singular. Suppose C is singular. If C is singular, what does that mean? Well, that means it has a null space. That means there's a homogeneous solution. That means there exists a non-zero vector, D, such that CD equals 0. That's one of the equivalent conditions of C being singular. It has a homogeneous solution. Okay? Now, if C has a homogeneous solution, then I can multiply this equation MS equals MTC on both sides by the vector D. So MSD is going to be MTC times D. If I do some associative law, I get MT times CD, which is MT times 0, which is 0. That means MS times D is equal to 0. That means the columns of S are not linearly independent, right? Because this here is actually a linear combination of the columns of MS. Now that's a contradiction because we know that the columns of MS are linearly independent. So we get a contradiction here. So just do that. Okay. That supposition is not correct, and it didn't take it, so let's try again. Why didn't it take it? Go. Okay. All right, so C is not singular. C is not singular. C is not singular, and it's an n by n matrix. That means that C is invertible. If C is invertible, I can multiply both sides of MS equals MT times C by C inverse. So if MS times MT equals MT times C, multiply both sides by C inverse. Because of the associative law, C cancels with C inverse, and I just get MT on the right-hand side. Right? So MSC inverse is equal to MT. What does that mean? Let's write it out again in terms of the columns. That means that the columns of MS times this matrix C inverse give me the columns of T. Now, I can break this equation up column by column. Again, each column of this matrix multiplication is a linear combination of the columns of S. That means that each column over here is a linear combination of the columns of S. What does that mean? That means that all of the vectors T are in S. All the basis vectors of T are in S, and that means T is contained in S. So that's the complete argument, that if you have two subspaces and one is contained in the other and they have the same dimension, they are in fact the same subspace. Very useful fact, very intuitive fact, but here you have a proof, a formal proof. Okay.